Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the binary eutectic phase diagrams. So as we discussed in the previous session, what is the importance of the phase diagram we have discussed, and based upon the phase diagram, we can easily identify what are the different mechanical properties as well as the chemical properties, and also how to identify the composition depending upon the temperature based upon the type of phase diagrams. We have seen the unique unary phase diagram as well as binary phase diagrams. So like this, in the binary eutectic also we have the phase diagrams. So how to draw these phase diagrams in the type of these eutectic type of systems. So before going to draw the eutectic phase diagrams, we have to know what is eutectic system. So if you see the definition of the eutectic system, the material which is easily melted with each other, then the type of system is called as eutectic. Now here, if you see this, another type of common and relatively simple phase diagrams found for binary alloys is the copper silver system. If you see the copper silver system, which is a eutectic type of thing. Why? Because these two metals can mix easily. So these are easily melted with each other. So that's why this system is called as a eutectic system. Eutectic system is nothing but the system in which easily melted. Okay, so that's why we are considering an example of the copper and silver in this system, and we'll draw the phase diagram for this and identify what are the different phases present in this, and also what are the different types of compositions we can have with respect to the temperature. Now if you see here, a number of features of this phase diagram are important and worth noting. So what are the different types of phases present in these types of eutectic system of the copper and silver? First three single phases are regions which are found in the diagrams are alpha, beta and liquid. So alpha, beta, liquid, these are the notations what we have discussed in the previous sessions. So these notations represents for the single phase. So what is that? Alpha, beta and the liquid. So these are the three we can see here in the phase diagram. We see clearly here if you can find the alpha region and the other beta region, you can see in this region beta and also the liquid. So how many here we are having? 1, 2 and 3. So total we have 3 single phase regions available in this eutectic system. So the system which is having only one type of phase is called as a single phase. So in the previous sessions also we have discussed the system can be having one or more than 2 phases. So if a system is having a single phase, then it is very easy for us to find out the composition as well as temperature by dropping the vertical and horizontal lines along the x and y axis. And if the same system is having 2 phases, that means more than 1 phases, what we have to do, we have to use the tie line method. With the help of the tie line process method, we have to find out what is the composition as well as the temperature at the particular point. So in this case, now we have the total 3 single phases which are available in this binary eutectic system of this phase diagram of copper and silver, in which we have alpha, beta and liquid as shown in this figure. Clearly these are 3 single phase regions available. Now this is how the copper silver of the binary eutectic phase diagram represents. So here you can see clearly at this zone we have the alpha region which is a single phase. So wherever you find these single notations, this represents for a single phase region. So alpha here you have one, and the liquid you have the second one, and the beta you have the third. Okay, so totally you have alpha, beta and liquid. So total 3 single phases you have. Okay, now coming to the, if you see this phase diagram clearly, so what are the other things you can easily find out here? Apart from alpha, beta and the liquid zone, you have alpha plus liquid. That means you have a two phases in this region. So in this complete region from A, B to E, you have two regions. So that is alpha plus liquid. Okay, so two different phases you can find at this region. Similarly, at this place also, beta plus L. That means you have one more two phase region at this E, F and G. So totally how many phases you have here? 1, 2, 3, 4 and 5. Here you have alpha, beta and liquid as single phases, and alpha plus L and beta plus L, you have two phase regions. Okay, so totally you have three single phases and two double phase regions. Two phase regions you have, that is the alpha plus L, beta plus L. So this is how you have to draw the phase diagram of the given type of any system which you have. So in this system we have taken an example of the copper and silver. So these are easily melted. That's why it's called as a eutectic system. Now here the alpha phase is a solid solution which is having a rich copper. Now if you see here at the x and y axis, around the x axis you have the percentage of copper. It starts with 0, slowly increases and reaches to 100. Similarly, along y you have the temperature. It is starting with 200 and reaching up to 1200 degrees centigrade. So this is how you have to draw the phase diagram with respect to x and y axis. In the previous also we have taken the basic example of the water and sugar. So with the help of the water and sugar we have drawn the phase diagram, and also we have considered the water from the three phases regions we have seen, that is the solid, liquid and vapor conversion, with the help of the pressure and compression graph. In this case also we are considering x and y axis, with x axis as a composition percentage and y axis as temperature. So again, what are the composition we are taking? Since it has to be 100%, at what point, at whichever point we are identifying, it should be 100%. As we have seen in the previous classes, the percentage of the sugar and water at any point, if you consider, it has to be 100. Okay, in the same way, in this also the silver and copper we are taking. So if you see at any point in between, the total percentage should be, the total weight percentage of the copper and the silver should be 100. Now here it starts with 0. So what is the other component? See here you have the rich copper, that means 100% of copper you have, 100% weight of copper. That means there is a 0% of the other end, silver. Okay, 0% of weight percent silver. So slowly you're increasing the percentage of the silver from 0 to 100, and from the percentage of copper is slowly decreasing from 100 to 0. So that is how you have to give the composition weight percent. Why? Because at any point, if you see here the 20% of what? 20% of silver. So what is the remaining percent? It has to be 80%. So 80% of the copper should be there. Like this, if you go on, it is reaching 100% of silver and 0% of copper, like this. Okay, so this is how you have to represent the x-axis of the composition of the silver as well as the copper in this direction, and along the y direction we are taking the temperature. Okay, now like this, here you have the complete 100% of copper, that is the pure copper is available at this zone. There is no any other impurities available here. The complete 100% rich percentage of copper is available at this point. Why? Because there is a 0% of silver and 100% of copper is available at this point. That's why you can find the rich in this copper. That is the solid solution which is having the rich in copper. And of course, it has a silver solute as a component and it has a FCC type of crystal structure. So this is having the face centered cubic structure. If you see the cubic face structure of this, the structure of the element at this point, you can identify the FCC type of crystal structure. And of course, the beta phase region of the solid solution, which is having FCC. So alpha is also having the FCC type of crystal structure, and beta is also having the face centered cubic structure. Both the solid solutions which is having the FCC type of crystal structure. But what is the thing it is happening here? The rich, that is the high percentage, is available at this alpha of copper, and beta you have the silver. The pure silver can be available at the beta zone and the pure copper is available at the alpha zone. So that is how you have to identify what is the percentage. So alpha is having 100 weight percentage of copper and beta is having 100 weight percentage of silver. So this is how you have to identify. So this is the importance of the phase diagram, so that you can identify with the help of these phase diagrams what is the composition. So what is the purity of the element with the help of these phase diagrams only. So that's why it is the drawing of the phase diagram, understanding the concepts of phase diagrams are very, very important in describing or your characterizing of any type of element which is available. Now the solubility in each of these solid phases is limited. So we have seen the boundaries in the previous sessions, the boundaries. So what are the boundaries? If it crosses the boundary, it slowly changes its phase from one phase to other phase. Okay, that is the solubility limit. For every type of system, you have the phases, different phases region depending upon the temperature. In the same case, in this also the copper and silver of the Eutectic system also is having the different phase regions. Okay, if you cross the boundary lines, what is happening? Slowly it is converting from one phase to other phase. So how these conversions are happening can be studied with the help of these phase diagrams. Okay, now if you see here, the solubility in each of these solid phases is limited in that a temperature below the line BEG. So what is happening? If you see the line BEG, so this is the BEG line. So BEG. So this is the BEG line. Only limited concentration of silver is dissolved in the copper. So very, very limited amount of the silver is dissolved in the copper. So why? Because you have the high percentage of copper in this and the very less amount of silver is being dissolved in this copper. And the same, similarly, the same thing, the copper in silver also, same reverse case. So below the line, what is happening? You are having the less amount of silver is being dissolved in the copper, and similarly above the BEG line, what is happening? Less amount of copper is being dissolved in the silver. So that is the difference you have to know. That's why this is the line, this is the solubility line, which is called as a limited concentration line. So BEG curve, from this BEG line we can tell that how much amount of the silver or how much amount of copper is being dissolved in the other respective element. So this is how you have to identify from these phase diagrams. Now the solubility limit of the alpha phase corresponding to the boundary line, which is labeled as CAB. If you see the graph or the curve in the phase diagram, if you see this curve CBA or CAB curve, if you see this curve, so what is happening here? This is limited. This is very limited line. Okay. Now between these, what is happening? Alpha by alpha plus beta and alpha by alpha plus L regions are there. So that is what this region is connected to this, and again the alpha plus L is connected to alpha. That's why this line is solubility line is limited to the phase regions of alpha, in which you can identify the line CAB, which is corresponding to alpha by alpha plus beta and alpha by alpha plus region. So these are the regions what you can see here, and these are linked up with this alpha region. Then what is happening here? It increases with the temperature to a maximum of weight percentage of 779 at point B. So what is happening? Slowly this curve you can see identify it's being increasing. Up to what point it is increasing? At point B. So at this point B, what is the temperature? If you draw the horizontal line at this point, so you can get as 779 degrees centigrade. So what is happening here? 779 degrees centigrade. And if you see the weight percentage, so what will be the weight percentage here? The weight percentage will be 8 weight percentage of silver. Is it not? If you slowly drop here, at this point, it starts with 0. At this point, you can have the weight percentage, okay, of silver is 8. So that's why we are writing as 8 percentage of silver. So at this point, you have 8 percentage of 8 weight percentage of silver. And what is the remaining? 92 percentage of copper. So like this, you have to balance. At any point, if you see along the phase diagram, it has to be balanced. It has to be 100 weight percentage of both. Why? Because since this is a binary Eutectic system, that's why the wherever the composition of is seeing, that should be a 100 weight percentage. So at this point, you have the 8 percentage of silver. So the remaining will be 92 weight percentage of the copper. Similarly, if you see the curve also along this point, slowly that HGF also if you see, so slowly it is also being increasing and reaching to point G and again coming back to F. So again, if you draw the horizontal and vertical lines, you can see the weight percentage. So what is the weight percentage at this point also can identify similarly. Now this ABC line or CAB line, if you see from here, it starts with 0, slowly reaches to the maximum point. So this is the maximum solubility point. It reaches to point B and again slowly it is coming back to the 0 position. At what temperature? It is at 1085 degrees centigrade. So this is the temperature at point A you are seeing. So like that, you have to identify at what temperatures, so what is the weight percentage of these Eutectic systems, and also what is the composition corresponding to that temperature also can be identified with the help of these phase diagrams. Now if you see in this reverse case of this thing, what is happening at a temperature of 779 degrees centigrade, that is at this point line, so you can see here 779 degrees centigrade, the solubility line separating the alpha and alpha plus beta, is it not? If you see here clearly, what is happening here? This line is being separating the alpha and alpha plus beta. So this is the line, separation of the line for these alpha and alpha plus beta. Okay, so this region is called as a solvus line. So this line which is being divided by the alpha and alpha plus beta, so this curve or this line is called as a solvus line. And the boundary AB, so this is the boundary AB, this is for alpha and alpha plus L. So what is happening here? This BEG line is very, very important. So what is happening? This BEG line, so this BEG line is trying to give the information of how much amount of silver is being dissolved in the copper and also how much amount of copper is being dissolved in the solid. And also what is the difference between these alpha and alpha plus beta and alpha plus L. So how it is being divided. So this BEG line is very, very important. At 779 degrees centigrade, we are getting this separation of the line. So this line is giving the information about the solvus line as well as the solidus line. Okay, solvus line is nothing but how much amount of the liquid is being solved into this. Okay, so that is the line which is below the 779 degrees centigrade, that is the solvus line, and above the 779 degrees centigrade you are getting the solidus line. So these are the two things you can identify from these phase diagrams. Next, in a similar way, so this we have studied for the alpha. In a similar way, if you go to the back of the entire right portion of the phase diagram, you can see the beta region. The same thing, beta region is also having the curve from H, G, F. Okay, this is the curve what we have. So from this curve also, we can tell the how much amount of thing is being solid is and solubility. So below the BEG line again you have this is the solvus line, and this is the solidus line. So it is similar to exactly for the alpha region as well as the beta region also. So in the both the cases we have the solvus line as well as the solidus line, and how we are getting these line with the help of the separation line of the BEG curve, which is at the 779 degrees centigrade. So this temperature is very important. At temperature 779 degrees centigrade we are getting the BEG line. So this separation line gives us the information about how much amount of the copper and silver are being dissolved in the respective regions at what temperatures also. Similarly, if you drop the vertical and horizontal lines, you can find out the temperature as well as the composition at this point. So almost you can get the 90% of silver at this point if you identify. So this you can see here 91.2 weight percentage of silver, and the remaining will be somewhat 7.8 weight percentage of copper. Why? Because the copper percentage is being reduced. Since it is increasing, it is starting with 0, that is the 100% of copper, that is the pure copper. Slowly after reaching to the maximum limit, what is happening? The complete solubility of the copper is being inside to the silver. That's why there is a less weight percentage of copper, because completely it is being solubility in the silver, and you can get the high percentage of silver at this junction, and you will get very less percentage of copper. That's why the weight percentage is 91.2 of the silver, and the remaining will be 7.8% of copper. So this is how you will find out the weight percentages. Now in this phase diagram, what is happening? The BEG line, the horizontal line we are seeing in this BEG, the phase diagram, this is parallel to the composition axis. If you see this, so exactly this BEG line is parallel to your composition. Okay, so both are parallel to each other. These two lines are parallel to each other. Now, what is happening here? The composition axis and extents between these maximum solubility portions may also be considered as solidus line. So, as we see for this alpha and beta, for both the regions we have the solvus and solidus lines. So this is how we can get the equilibrium between these BEG curves of the alpha and beta regions. So there are also three phase regions found for the copper silver phase diagram. So what are the three two phase regions you have? So if we have seen earlier, alpha, beta and liquid. So these are three single phase regions. Similarly, if you observe here, you have alpha plus L, alpha plus beta and beta plus L. So what is happening here? Again you have alpha plus L, alpha plus beta and beta plus L. Here you have three two-phase regions. So total you have three single phases as well as three two-phase regions are also available in this phase diagram. So that is how you can easily tell that the silver and copper are having total number of how many means 6 phases you have, in which you have 3 single phases and 3 double phases you can tell. So this is all the information we are getting from the help of the phase diagram only. So the alpha plus beta, alpha plus L, beta plus L, these are the three two phase regions which are available in this phase diagram. And also if you want to find out the composition corresponding to these regions, what you have to use? We have to use the Thailand method process. So how you to draw the Thailand method process means, suppose if you want at any point at this junction, suppose X, there is a single phase. So what directly I can draw the vertical lines along X and Y. I can get what is the temperature at this point, what is the composition at this point also I can get. But in case of double phase, suppose some y point I want to have. So since it is having a two phases in this region, I have to use a tied-end method process. So what is the tied-end method process? I have to draw a line which passes through this point and intersect these two regions. At these two regions, it has to intersect. That means at this point, y1 and y2. What are the point I have? This y. Through this point, it has to intersect these two regions. So from these two regions, again, I'll draw the vertical lines and also the horizontal line, and I'll get what is the temperature as well as the composition at these 2 points I'll get. So this is how you can find out the composition as well as the temperatures if it is having a two phase regions. So that is the importance of the phase diagram. Now a silver is added to copper and the temperature at which the alloy becomes totally liquid and which decreases the liquidus line AE. So if you see the line AE, so where is the line AE? So this is the line AE, you see. So what is happening here? As silver is added, so we are adding the silver to the copper. So what is happening? Slowly the temperature at which the alloy becomes totally liquid. So here you are getting complete total liquid thing, and what is happening? Slowly it is being decreasing since it is being in a liquid state. So slowly it is being decreasing from this point to point E. So like this you are getting the decrease of this reduction of the liquidus line. That is the melting temperature of copper is lowered by addition of silver. So what is happening? Here we are getting the melting temperature of copper is lowered. So if you want to reduce the melting temperature of copper, what you have to do? You have to add the silver into the copper. So here you have a high amount of melting temperature of copper. Now this temperature, it is being reduced slowly when there is an addition of silver into the copper. So at this point, so you can see almost from 1100 degrees centigrade to it is falling up to 779 degrees centigrade because addition of silver into the copper will be reduction in the melting temperature of the copper line. Similarly, if you see the line Fe, so this also exactly opposite to this. So what is happening in the previous case? The copper melting temperature is being reduced with the addition of silver. In this case, the silver melting temperature is reduced by the addition of the copper. Just exactly opposite. So how it is being reduced? It is being reduced from almost 1780 degrees centigrade to 779 degrees centigrade. So just opposite to each other. Addition of copper will reduce the melting temperature of the silver, and similarly addition of silver into the copper will reduce the melting temperature of the copper. So this is how you are getting the information of the melting temperatures also with the help of these phase diagrams. Now if you see an example to find out the phase present and also to compute what are the phase compositions, if it's just consider an example, practical example. So if you really see 40 weight percentage of tin with 60 weight percentage of lead alloy at 150 degrees centigrade. So this is the composition what we have given of the lead and tin, and from this at 150 degrees centigrade, what are the phases present and what compositions of the phases are there. So these two we need to find out with the help of these data. Now if you see here the location of this temperature composition and the phase diagrams, we will see the phase diagram. So this is the phase diagram what we have for the lead and tin. So this is how you have the phase diagram. Now in this case you have to find out the phases present. So here you have alpha, alpha plus L, beta plus L, beta. Almost similar to your copper and silver phase diagram. So here you have 1, 2, 3, 4 and 5. That means 2 single phase regions and 4 two phase regions. So total how many you have? 2 plus 4. 2 plus 4, you have 6 phases. Total you have 6 phases. 1, 2, 3, 4, 5 and 6. So total you have 6 phases, in which 2 are single phases and 4 are two phase regions. So that is how you have to find out. Now here what is happening? They have given some weight percentage. With the help of those weight percentage of the lead and tin, we have to find out what is the composition. Now because two phases are present at this junction, at the composition at this point, we are getting the two phases, since alpha plus beta. So what you have to do? I have to draw a tie line which passes through this point and identify what are the compositions along this point. Okay, so C alpha and C beta. So how much you are getting? Approximately 98 weight percentage of tin and 2 weight percentage of lead at this point. And similarly at this point is also how much you are getting? About 11 weight percentage of tin and 89 percentage of lead. So that is the identification of the composition corresponding to that point when it is having single phase. But if this point, the same point is somewhere at this point, directly we can draw the horizontal and vertical lines and we can find out the composition. But since this point, what are the composition they are asking, this point is lying between the two phase region. That's why we are using a tie line process, and with the help of the tie line process we are identifying what is the composition along those 2 points. This tie line has to be connected to those two phases regions which has to pass along this point. That's why along this point B, a line is being tied between these two phases, and we are trying to identify what is the composition corresponding to this by drawing the horizontal and vertical lines for the composition and horizontal line for the temperature. So this is how you have to identify. And these are some of the references where you can find out the information about the phase diagrams of the binary eutectic systems, and what is the important of these eutectic systems, or what is the definitions of these eutectic. Eutectic is nothing but which are easily melted with each other. Okay, so this eutectic systems give us information about the melting temperatures of the materials, as well as the how it is being varying from one phase to other phase, and also we get the information about the how many phases are present, whether it is single phase or double phase. Okay, so all this information is very useful in designing any type of product or selection of any type of materials. So these are some of the references where you can get the information. That is, first one is the Sydney Heavener Introduction to Physical Metallurgy. The second one is Essential of Material Science Engineering by Donald. The third one is Material Science Engineering by Kodigiri, and the last one is Material Science and Engineering by William Castler. So these are some of the references where you can get the information about all the basics of the phase diagrams of the eutectic systems, and also how to identify the compositions with the help of these tie line process, whether it is single phase or double phase, and what is the importance of drawing these phase diagrams. We can get the information from these references books. Thank you for the session.
Like, share and subscribe. Hit the bell icon for more updates.